आइए टायर बदल लीजिए।
Okay, hello everyone. So obviously my body is not like that of our Bollywood stars, so that I can lift the car with my hands, but still I have a better thing to do. I have a better way to lift this car. What I have is I have a screw jack, and with the help of this screw jack I am going to lift this car. How? I am putting a lever on it and I am applying a force on this. And with this force, when I am rotating this, with this force, the wheel, as you can see, is lifted up. Getting this or not? Okay, so such a device is known as the simple machines, the device which multiplies the force. I am applying a very little force, and that is multiplying the force in order to lift the weight of this whole car. Such device is known as simple lifting machines. When I am putting two simple machines together, it becomes a compound machine. For example, in this device only, first is the screw jack. First machine is the screw jack, which in itself is a device, in itself is a machine. Second machine I am putting is this lever, because if I apply the force from here, it will be very difficult for me to apply the force. Okay, so what I am doing is I am putting a lever on this and I am applying a force, so it becomes very easy. Okay, so such device is known as compound machines. Such device is known as compound machines, in which two or more simple machines are used. Okay, first thing. Now the weight of this car which is to be lifted is known as load, which we generally denote by W, and the effort, the force which I am applying on this, the force which I am applying on this lever is nothing but the effort, which we generally denote by P, and the ratio of this load to effort is nothing but the mechanical advantage. The load which is to be lifted and the effort applied, the ratio of that load to effort is nothing but the mechanical advantage. Next term is the velocity ratio. Now what actually is this velocity ratio? It is the distance moved by effort, the ratio of distance moved by effort to the distance moved by load. For example, in this device only, when I am rotating this by one complete revolution, when I am rotating this lever by one complete revolution, that means suppose the length of this lever is suppose L. So when I am rotating this, the total distance covered by this lever is nothing but 2 pi L, the whole circumference which is getting covered by this particular lever. And with that one rotation, the screw jack will be lifted by one pitch, as you all know. With one rotation of this complete lever, the screw jack will be lifted by one pitch. Okay, so the distance travelled by effort, which is nothing but 2 pi L in this particular case, to the distance travelled by load, which is nothing but pitch of the screw, that ratio is nothing but the velocity ratio. Now next term is the efficiency of the machine. Now what actually is the efficiency of machine? Efficiency is defined as the ratio of output work done to input work done. Now suppose we have this car which is having a weight W, we are assuming all the wheels to be lifted up, assuming that, and the weight of this car is suppose W, that means the load to be lifted is capital W, and the distance by which it is getting lifted is suppose small d. So what actually is the work done by this particular machine? Work done is force into distance or force into displacement, so that will be equal to W into small d. Now what work I am giving it? I am applying a force P, the work input we are saying, I am applying a force P on this lever, and with this P force, suppose this lever is getting displaced by an amount, suppose capital D, which we have already seen that capital D is equal to 2 pi L and small d is equal to pitch. So capital D, by distance capital D, it is getting displaced. So what will be input work done? Input work done is nothing but P into capital D. Okay. Now what will be efficiency? Efficiency is nothing but output upon input. So efficiency will be equal to W into small d upon P into capital D, or you can say W by P upon capital D by small d. So this efficiency is equal to mechanical work upon velocity ratio. This is nothing but the efficiency. Okay, so if the efficiency is 100%, that means if the friction is not present at all, then what will happen? Then mechanical work will be equal to the, mechanical advantage will be equal to the velocity ratio in case if the friction is absent. Clear or not? Okay. Okay, so that was just one of the example of the lifting machines, the screw jack. Likewise, we have many lifting machines which we use in our daily life. For example, lever, for example, pulley system, the worm wheel, differential worm wheel, etc. These all are different, or you can say the wedge is also a lifting machine. The inclined plane is also a lifting machines. So these all are the examples of different examples of lifting machines. So in this particular unit, we will be focusing on those type of lifting machines, different types of lifting machines. We will be determining the mechanical advantage and velocity ratio for different types of lifting machines. Getting this one? Okay, so let me explain you with the help of very simple example. The same thing which we understood with the help of that screw jack. Let me make it more simple. Suppose I have a weight W and I want to lift this weight. Okay, so what I will do is I will make a lever, I will make one pivot, okay, and I will place the load W1 or W at one end which is to be lifted, and I will apply the force, the effort from the other end. Okay, now this is something which we use, which we see in our daily life. If you have seen a coolie lifting the weights with the help of his cart, he is using the same principle. Okay, so what I am doing is, suppose this length is L1 and this length is suppose L2. Obviously, you can see from the figure that L1 is less than L2. Okay, so when I am applying a load P here, the moment about this pivot of this load W and this load P will be equal, or you can say moment about this pivot will be equal to 0, or you can say W into L1 will be equal to P into L2. Okay, so from here you can get the value of this P, which is equal to W into L1 by L2. Okay, and as we know that L1, because L1 is less than L2, you can see from the figure, therefore obviously this P will be less than W. That means effort which is to be applied is much less than the load which is to be lifted. Okay, such machines, as I told you, is known as the lifting machines. Okay, next concept I told you about the velocity ratio. Now what is velocity ratio? It is the distance travelled by the effort, ratio of distance travelled by the effort to the distance travelled by load. Now on applying this particular load, particular effort P, suppose this lever is displaced by an amount, suppose capital D. Okay, and this load, the weight is suppose displaced by an amount small d. Okay, and it can be easily determined. Suppose I have the angle theta, then I can determine this arc which is equal to angle into radius. So this will be equal to L2 into theta. Okay, so from here I can determine the velocity ratio. So this velocity ratio will be equal to distance travelled by effort to distance travelled by load, which is equal to capital D by small d. Getting this or not? Okay, next concept I told you about the efficiency of the machine. Now what is efficiency? As we all know, efficiency is nothing but the ratio of output work done to the input work done. So this efficiency will be equal to what? Output upon input, output work done upon input work done. Now what is output work done by this machine? This machine is displacing this load W by an amount small d. So work done is nothing but load in force into displacement. So this output work done is nothing but capital W into small d. Getting this? What will be input work done? I am applying a load P, and as a result of that, this is getting displaced by a distance capital D. Okay, so input work done will be equal to what? This will be equal to P into capital D. Getting this? So this can be written as what? W by P upon capital D by small d, or this can be written as W by P is nothing but mechanical advantage, capital D by small d is nothing but velocity ratio. So from here you get what? Efficiency is equal to mechanical advantage upon velocity ratio. Very important formula. The efficiency of machine is nothing but mechanical, the ratio of mechanical advantage to that of the velocity ratio. Velocity ratio. Getting this or not? Okay. Now, suppose if the friction is not acting on the machine. Now what will happen? If the friction is not acting, then the efficiency will be equal to 1. Because friction is not acting, the efficiency will be equal to 1. For no friction, efficiency will be equal to 1, or you can say mechanical advantage will be equal to velocity ratio. Therefore, for an ideal machine, the mechanical advantage becomes equal to velocity ratio. Okay. Now, suppose if the friction is acting on the machine, then what will happen? Now, because of the friction, what will be the effect on this effort P? The effort which I had to applied without friction will obviously be less than the effort which I have to apply with friction, because some amount of effort, some amount of work is lost in overcoming the friction. Okay. So, now if the friction is acting on this particular machine, the effort required by us will be obviously more than that of the ideal effort. Getting is not? Or you can say, if friction is acting, the effort required P actual will be greater than the ideal effort which is to be required for an ideal machine. Getting this now? Okay. So, what will happen to the mechanical advantage? Mechanical advantage is nothing but load upon effort. Okay. Now, since this effort is getting decreased, since this effort is getting increased, therefore, mechanical advantage will be decreased, because the actual effort is greater than that of the ideal effort. So, actual mechanical advantage will be less than the ideal mechanical advantage. Getting this point or not? Because actual effort required is more than that of the ideal effort. Therefore, actual mechanical advantage will be less than that of the ideal mechanical advantage. Okay. Now, what will happen to the velocity ratio? Will there be any effect on velocity ratio of this friction? No, there won't be any effect, because velocity ratio does not depend upon this motion. Velocity ratio is just depending upon the geometry. Velocity ratio is what? The distance travelled by P to the distance travelled by W. So, this is just depending upon the geometry of the machine. So, that will not be affected with friction. That means, velocity ratio of actual machine will be equal to velocity ratio of ideal machine. Okay. Now, what does this conclude? The efficiency, which is equal to mechanical advantage upon velocity ratio. If the friction is not acting, then mechanical advantage is equal to velocity ratio. If the friction is acting, the mechanical advantage is decreasing, velocity ratio remains same. Therefore, if friction is acting, then obviously the efficiency of the machine will be less than 1 for obvious reasons. Getting this not? Okay. So, if the friction is acting, efficiency is less than 1. If friction is not acting, efficiency is equal to 1. If friction is acting, actual effort required will be greater than that of ideal effort, and which will decrease the mechanical advantage, but because velocity ratio remains same, therefore, the efficiency decreases. Clear or not? Okay. Now, write down note. For ideal machine, since no friction is present, therefore, efficiency is equal to 1 and mechanical advantage is equal to velocity ratio. Mechanical advantage of any simple machine is always less than mechanical advantage of its ideal model. Velocity ratio of any machine and ideal machine is always equal. Velocity ratio depends upon its geometrical features, and it is assumed that there is no lost motion on input and output side due to slippage, etc. Okay. So, velocity ratio will be same, because we are assuming that there is no slippage in input and output. Okay. If there is slippage, then obviously the velocity ratio will change, but not because of friction. Clear or not? Okay. Next topic is the frictional losses. So, as we have seen, suppose we want to lift the weight W and we are applying a load and effort P on it, okay, such that this P is displaced by an amount, suppose capital D, and this W is displaced by an amount, suppose small d. That means, input work done, as we have seen, is nothing but P into capital D, and output work done is nothing but W into small d. Now, the question arises, if the friction is acting, now will this input work done will be equal to output work done? Obviously not, because the work we are giving through our effort, some of that work will be consumed in overcoming the friction, and remaining amount of work will be transferred to the as an output. That means, input work done is obviously greater than that of the output work done if the friction is acting. Okay, so what will be the frictional losses now? So this frictional loss will be equal to input work done minus output work done. Okay, now what is this input work done? This is nothing but P into capital D minus output work done is nothing but W into small d. Getting this now? Okay, now how much effort is lost in the friction? Let us determine that thing. P friction, because we are applying certain effort, certain load, and some of that effort obviously is getting lost in the friction. So this will be equal to P actual minus P ideal. Why this is P actual minus P ideal? Because actual effort required will be more as compared to the ideal effort. Okay, because some amount of effort is getting lost in the friction, so I will have to apply more effort. So actual effort is obviously greater than the P actual is greater than P ideal. Okay, so the difference between P actual and P ideal is nothing but the P friction. Okay, and as we know that efficiency is equal to what? Mechanical advantage upon velocity ratio, and if this is considered as an ideal machine, this will be equal to 1. Okay, or you can say for an ideal machine this will be equal to W upon P ideal, ideal effort, upon velocity ratio is equal to 1, or you can say from here P ideal will be equal to W upon velocity ratio. Okay, so if you want to determine the ideal effort for a given amount of load, the ideal effort for a given amount of load which is to be applied is nothing but W upon velocity ratio. Clear or not? Okay, now coming to the load part. Now what will happen to the load to be lifted if the friction is acting? Now if the friction was not acting, obviously this machine would have been capable of lifting more load. That means, and if suddenly if the friction is acting, this machine will obviously lift less load. This means that W ideal will obviously be greater than W actual. P ideal was less than P actual, but W ideal will be greater than W actual. Why? I told you, because if the friction is not acting, then this machine would have been capable of lifting more load. And if the friction is acting, this is actually lifting less load. That means W ideal is less than W actual. So what will be W friction? The difference between the two. That means this will be equal to W ideal minus W actual. Okay, so from here you can determine this W ideal. What is W ideal? Efficiency, as we know, is mechanical advantage upon velocity ratio. So in this case, this can be written as W ideal upon P upon velocity ratio, and if this is an ideal machine, efficiency is equal to 1, or you can say this W ideal is equal to P into velocity ratio. Okay, so these are two important conclusions which we got. P ideal is equal to W by velocity ratio, and W ideal is equal to P into velocity ratio, and with the help of this we can determine the frictional losses. How much effort is lost due to friction? So from here this P friction will be equal to P actual minus P ideal, which is equal to W by velocity ratio. That's it. Okay, how much load is lost because of friction? That is equal to W actual minus W ideal. So this W friction, which is equal to P into velocity ratio minus W actual. That's it. Okay, so these are the frictional effort loss and frictional load lost. Getting this or not? Okay, now the relation between load and effort, the relationship between load and effort. Okay, so this load and effort follows a linear relation. That means this P is equal to what? M into W plus C. P is equal to M into W plus C. That means if I plot the y axis will be load, x axis will be y axis will be effort, x axis will be load, and as we all know y is equal to mx plus c. This is the equation of a straight line, y is equal to mx plus c, and here x is independent axis and y depends on x. That means the independent quantity is taken always in x axis. Load is independent, effort depends on load, so it is dependent quantity. Getting this? Okay. So, this is following a linear relationship, y is equal to mx plus c. So, from here this curve is nothing but P is equal to m into w plus c, okay, where m is slope of this straight line and c is nothing but the intercept in the y axis. That means this quantity is nothing but c. Getting this now? Okay. Now, what will happen if the load is 0? Now, if the load is 0, if the load is becoming 0, this P, if W is equal to 0, then this P becomes equal to C. Now, what is the meaning of this? If load is 0, then also we have some effort. Now, why is this effort? Because of the frictional losses. That means this C, this constant, this intercept C is nothing but this is accounting for the frictional losses. Getting this or not? Okay, so if we have an ideal machine in which there is no frictional losses, so if we have the ideal machine, this frictional loss will be equal to 0. So, for ideal machine, this P is equal to m into w. Okay, so for this ideal machine, we have a straight line which is passing through the center. Getting this or not? Okay. So, write down a note. If W is equal to 0, P is equal to C, that is C represents frictional resistance of machine. Therefore, graph for ideal machine passes through the origin. Next is the relationship between efficiency and resistance to overcome. Relationship between efficiency and resistance to overcome, or you can call it as W. W is nothing but the resistance which is to be overcome. Okay, so the relationship between efficiency and W, the curve is like this. Okay, this is 100% efficiency, that means efficiency is equal to 1 at this particular point. So, you can observe one thing from here, that obviously as the load is increasing, the efficiency is increasing, but the rate of increase of efficiency, as the load is increasing, the rate of increase of efficiency is decreasing. As you can see, the slope is decreasing. Okay, and what is this slope? That slope is nothing but the rate of increase of efficiency with respect to load. Okay, so because this slope is getting decreased, therefore the rate of increase of efficiency decreases with this load. Okay, so write down the note. Rate of increase of efficiency goes on decreasing with increase in load. Okay. Okay. Now coming to another topic, which is reversibility and self-locking. Reversibility and self-locking. Okay. Now, what is this reversibility and what is the meaning of self-locking? So, suppose I will explain you with the help of a pulley. Suppose we have this pulley, and for lifting a weight W, I am applying a load, suppose P. Okay. Now, the displacement by this effort is suppose capital D, and the distance by which this load is getting lifted is suppose small d. Okay. Now, if I release this load at this particular point, I am applying a load on this, and if I release this load at this particular point, what will happen? This will reverse. That means this weight will dominate, and this weight, which was actually here after displacement, this will come back to the original position. So, this is known as reversibility. That means the work which is done reverses itself. The work which I am doing on this weight because of this effort P, that is reversing itself. That is known as reversibility. Okay. Now, what is self-locking? Self-locking means it should lock at that particular point, like it happens in a screw jack. Okay. What will happen if the screw jack is not a self-locking machine? What will happen if I am applying a force? It has to stop there. If it is not stopping there, it will again return back and I will have to apply more force. As I showed you in the starting of this video, I was applying a force on it and I was just stopping there, and that screw was displaced by that much amount. So, that machine is known as a self-locking machine. Okay. And the machine which reverses itself is nothing but the reversible machine. Getting this or not? That means on removal of load, a machine in which on removal of load it does work in a reverse direction is called as the reversible machine, for example pulley. Okay. A non-reversible machine cannot do any work in reverse direction when the effort is removed. Clear or not? Okay. Now, coming to the condition of self-locking. Now, when can we say that this machine is self-locked? Okay. So, understand this thing very carefully. So, I am applying a load P, and because of this load, because of this effort P, this rope is getting displaced by an amount capital D. Getting this one? And some amount of that work, as I told you, is lost in the friction, and remaining amount of that work is utilized in lifting this weight up. Okay. Now, if this weight has to reverse, first consider the condition of reversible machine. If the weight has to reverse, then it will have to overcome the frictional resistance. Getting this one? That means the work done by this weight W, which is equal to W into D, this should be greater than the frictional resistance in order to reverse for a reversible machine. Then only it will be able to reverse. If it is less than the frictional resistance, then the machine will be self-locked. That means it is not getting reversed. Why? Because of the frictional resistance. Getting this not? Therefore, for a reversible machine, first is the condition for reversible machine. This W into small d, the work done by this load W should be greater than the frictional resistance. Getting this or not? Okay. Or you can say this W into small d should be greater than frictional resistance. We have seen the formula, which is equal to P into capital D, input work, minus W into small d, output work. Or you can say this 2W into D is greater than P into capital D, or you can say this W into D upon P into capital D is greater than 1 by 2. Okay. So, this W by P is nothing but mechanical advantage, this capital D by small d is nothing but velocity ratio. This is the ratio of mechanical advantage to velocity ratio, which is greater than 1 by 2, or you can say the efficiency should be greater than 1 by 2. This is for a reversible machine. Okay. And opposite will be the case for a self-locking machine. Therefore, what will be the condition of self-locking machine? For self-locking, this W into D is less than P into D plus W into D. Okay. So, for this self-locking machine, this efficiency should be less than 1 by 2 or less than 50%. Okay. So, this is the best way to check whether the machine is a self-locking machine or a reversible machine. If the efficiency is less than 50%, then the machine is self-locking machine, and if the efficiency is greater than 50%, then the machine is nothing but the reversible machine. Getting this or not? Okay. We will solve one question. In a machine whose velocity ratio is 6 and effort of 20 Newton was able to lift a load of 100 Newton. Find first efficiency of machine, effort lost in friction, and frictional load. Okay. So, what is given in this particular question? In a machine whose velocity ratio is 6, velocity ratio is given as 6, effort P actual is given as 20 Newton, and the load lifted, that means W actual, is given as 100 Newton, we have to first find the efficiency of the machine. Okay, so how can we determine efficiency of the machine? So for that, efficiency, as we all know, is what? Mechanical advantage upon velocity ratio. We have the value of velocity ratio, just determine the mechanical advantage. So this mechanical advantage is nothing but P by W, W by P, load per unit effort. So this will be equal to 100 by 20 upon velocity ratio is 6, which is equal to 5 by 6, or this can be written as what? 83.33%. Answer. This is first part. Getting this or not? Okay. Second, effort lost in friction. Okay. Now, how much effort is lost in friction? So for that, I told you. So P friction is nothing but P actual minus P ideal. Okay. And P ideal we can determine. I told you the formula is equal to W upon velocity ratio. Okay. So actual weight to be lifted is 100 Newton. Velocity ratio given is 6. Okay. So from here, this P ideal will be equal to 16.67 Newton. P ideal. Okay. So effort lost because of this friction we can determine from here. This is equal to P actual, which is equal to 20 minus 16.67. So this will be equal to 3.33 Newton. That's it. Second answer. Okay. Third point is nothing but frictional load. That means W friction we have to determine. So this W friction is nothing but W ideal minus W actual. Okay. And I told you how to determine this W ideal. So this W ideal is nothing but P into velocity ratio. So this will be equal to what? P is 20 into velocity ratio given is 6. So this will be equal to 120. So this W friction will be equal to 120 minus 100, which is equal to 20 Newton. That's it. Simple question. Answer. Okay. Okay, so very first topic, very first kind of lifting machine we are going to study is the pulleys. Now, what actually are the pulleys? Pulleys are the, I should say, most commonly used and most ancient type of lifting machine. You have already seen right from lifting of water buckets from well to lifting of heavy objects in industries through cranes. Everywhere pulleys are used. Now we are going to study about this pulleys. Now before actually studying about this pulleys, we have certain assumption. The very first assumption is that the pulley is weightless, and second assumption is that the pulley is frictionless. So we are assuming a weightless, frictionless pulleys, and now we are going to analyze this pulley. Okay. First start with a simple pulley. A single pulley, a weight is hanging at one end W, and we are applying an effort P at other end of the rope. Okay. Now if I draw the free body diagram of this particular weight, so we have this rope, and obviously in this rope a tension T will be acting, the weight acting downward. So the free body diagram will be like this. The weight is acting downward, the tension is acting upward. Okay. Now what will be the value of this tension? Because this is a frictionless pulley, so whatever we are applying, whatever effort we are applying, that effort P will be equal to T. Okay. So from equilibrium, this W will be equal to T, which is equal to P. That means W is equal to P. Now what will be mechanical advantage in this? Mechanical advantage, as we know, is load upon effort. Now since W is equal to P, so this mechanical advantage is equal to 1. For this simple pulley, mechanical advantage is equal to 1. That means the whatever load we are having, that much effort we will have to apply in this case of simple pulley. Okay. Now similarly, velocity ratio also we can determine. Now what will be velocity ratio? Now assuming zero slip, so suppose this is moving by a distance capital D, and this is moving by a distance capital D, and this effort is moving by a distance, suppose small d. Okay, because this is a single pulley, so this capital D will be equal to small d. Whatever the distance which rope is covering at this end, same distance rope will cover at this end, assuming no slip. Okay, so in this case velocity ratio will be equal to d by d, since capital D is equal to small d, so this is also equal to 1. So mechanical advantage is 1, velocity ratio is also equal to 1. Getting this? And if this is a frictionless pulley, then obviously the efficiency will be equal to 1 or 100%. Okay, now you might be thinking that there is no big deal about this pulleys, but when we are using the system of pulleys, this scenario will change drastically. Okay, we will see this. Now coming to the system of pulleys. Now the very first system is the first system of pulleys. We have three different system of pulleys. The first is the called as the, we have given the name as first system of pulleys. Okay, so we have this first system of pulleys. The arrangement of pulleys is like this. So we have a fixed pulley here. This pulley will not move, and we have the movable pulleys, three movable pulleys, pulley number 2, 3 and 4. Pulley number 1 is fixed and 2, 3, 4 are movable pulleys, okay, which can move vertically up and down. Okay. Now what actually is happening when I am applying a load P at the end of this rope which is wrapped around pulley number 1. So suppose the displacement of this rope is suppose y. Just understand this thing very carefully. I am applying a force P at the end and suppose the displacement is y. Okay. Now this end of the rope will also be displaced by y. Okay. Now this rope is wrapped around this pulley, pulley number 2. Okay. So at two sides of the pulley, this y will be distributed as y by 2 and y by 2. Getting this or not? Okay. That means this particular pulley will be lifted by an amount y by 2. Clear or not? I will explain it again. This force on the application of this force P, this rope is moving by an amount suppose y, and with this y, this pulley will move up by an amount y by 2, because this displacement y will be distributed on two sides, y by 2 and y by 2. That means the center of this pulley will lift by a distance y by 2. Getting this now? Okay. Similarly, because this is lifting by a distance y by 2, this rope will be lifted by a distance y by 2. Now again this rope is wrapped on two sides of this pulley. Okay. So the center distance of this pulley will be lifted by an amount y by 4, or you can say y by 2 square. Getting this? Just half. Displacement of this is half of this. Displacement of this pulley is half of this. Similarly, coming to this pulley, now the center of this is raised by a distance y by 4. This pulley is raised by a distance y by 4. That means this rope will be raised by a distance y by 4. Okay, so this y by 4 will be distributed among these two sides, and this will be raised by a distance y by 8, or you can say y by 2 cube. Getting this or not? Clear or not? Okay, that means displacement of effort is y, displacement of pulley 2 is y by 2, displacement of pulley 3 is y by 4, or you can say y by 2 square, displacement of pulley 4 is y by 2 cube, or you can say y by 8. Okay. So as the number of movable pulleys increases, this quantity will increase. This is because the number of movable pulley here is 3, that means n is equal to 3, okay, where n is number of movable pulleys. Okay. So the displacement of last pulley, or you can say the displacement of this weight W, this will be equal to 1 by or y by 2 raised power n for n number of movable pulleys. Getting this or not? If this is displaced by a distance y, then this load will be lifted by a distance y by 2 raised power n. Okay. So what will be the what will be the velocity ratio now? So the velocity ratio, as we know, is the distance travelled by effort to distance travelled by load. So this will be equal to y by 2 raised power n. Y gets cancelled out, so this is equal to 2 raised power n. So we get the velocity ratio for the first system of pulleys as 2 raised power n. Okay. And as we are assuming that the pulleys are frictionless, so efficiency will be equal to 100%. Therefore, mechanical advantage is also equal to velocity ratio, which is equal to 2 raised power n for first system of pulleys. Getting this or not? Okay, this is for an ideal pulley. Clear? Okay. Now coming to the second system of pulley. Next is the second system of pulleys. Okay, so this is the arrangement for second system of pulleys. We are considering 5 pulleys. Let's suppose the number of pulleys may be n. Okay, and a single rope, you can see one thing here, a single rope is wrapping this initially pulley 1, then to the last pulley, pulley 5 in this case, then to the second pulley, then to the fourth pulley, and then to the third pulley, and then it is fixed at this point. Getting this arrangement? Okay, and a weight is hanged at the end. Now let us draw the free body diagram of this lower block. Okay, so how will be the free body diagram of this lower block? So we have 2 pulleys and 5 ropes getting from this. Okay, so this is rope 1, rope 2, rope 3, rope 4 and rope number 5. This is the case as I told you for 5 number of pulleys. Suppose we have 6 number of pulleys, there will be 6 number of ropes here. Okay. Now as I told you that a single rope is wounded in all these pulleys. Okay. So the tension acting in all these pulleys will be same, will be equal to T suppose, and that T is nothing but equal to P. Okay. If I look at here, so the T for this pulley, this P is equal to T. Suppose the tension here is T, and the same rope is wounded in all the pulleys. So the tension in all the string will be same, suppose T, such that this T is equal to P. Okay. Here we have the weight acting downward W. Okay. Getting the free body diagram or not? Okay. So suppose this number of pulleys, this here we have considered 5 number of pulleys. Suppose the number of pulleys is n. Let's suppose number of pulleys are n. Okay. So we will have n number of ropes here in the free body diagram. Okay. So if I draw the free body, so if I put equilibrium equation summation of Fy is equal to 0, what I will get is n into T, n number of ropes into T is equal to W, or you can say n into P is equal to W since T is equal to P, or you can say W by P is equal to n. So this is nothing but mechanical advantage which is equal to n for this second case of pulley, second system of pulleys. Okay, and obviously if efficiency is equal to 1, then velocity ratio is also equal to n. Clear or not? Okay. Now here obviously we are considering the weight of pulleys as negligible. Suppose in question the weight of pulleys are also given. Suppose the weight of the lower part of this system, suppose weight of lower part of system is suppose small w. Okay, then what will happen? Weight small w will also be acting here. So from here n into P will be equal to capital W plus small w. That's it. Getting this or not? Okay, so this is the case for second system of pulleys. And as I told you, here n is the number of pulleys used. In previous case, n was the number of moving pulleys. That means total number of pulley was n plus 1. Here n is the number of pulleys. Whatever be the number of pulleys, you will get that much amount, that much rope here, that much tension here. Okay, so it will be n into T minus W is equal to 0, or you can say W by P is equal to n. Mechanical advantage is n. Getting this or not? Okay. Now coming to the third system of pulleys. Next system of pulley is the third system of pulley. Okay, so this is the arrangement for third system of pulleys. Okay, so we have suppose 4 number of pulleys. So different ropes are wrapping on different are wrapped on different pulleys. Getting this or not? So how much, whatever be the number of pulleys, that much is the number of ropes required in this system of pulleys. Okay. Now what actually is happening when I am applying this load W is to be lifted, and I am applying a load P at the end of this, suppose pulley number 1. These are 4 pulleys Okay. So, what will happen? A tension will be developed in this pulley, in this particular pulley a tension T1 will be developed, okay. And as a result of that, this will be, because of this a tension T2 will be developed here, T2 tension will be developed here, this is a different rope. Similarly, T3 tension will be developed here, T4 tension will be developed here. Okay, now considering the equilibrium of this particular block in which weight is hanged. Okay, so the upward forces which are acting are, the upward forces acting on this particular block is T1, T2, T3, T4, and downward force acting here is W. Okay. And suppose if we are having n number of pulleys, it will be up to Tn. Okay. So, applying equilibrium, so this will be equal to T1 plus T2 plus T3 plus up to Tn, this is equal to W, downward force W, first thing. Okay. Now, considering the equilibrium of this pulleys, individual pulleys, first consider the equilibrium of this pulley number 1. Okay, so, we have tension T, and because we are assuming this as frictionless pulley, this P will be equal to T1. Okay, so, tension T1 is in pulley number 1, the string of pulley number 1. Okay, so, we have the free body diagram like this. So, here we have tension T1, and here upward T2. Getting this not? Okay, applying equilibrium. So, what we will get is 2T1 is equal to T2, okay. Or you can say, since T1 is equal to P, so you can say T2 is equal to 2 times of P. Give this as equation number 1. Second, T1 is equal to P, this was equation number 2, suppose this is equation number 3. T2 is equal to 2 times of P. Okay. Now, coming to the equilibrium of this pulley. Okay. Now, what are the forces acting? The upward force is T3, downward force is 2T2. Okay. That means T3 is equal to 2T2. Okay. And as we know, T2 is equal to 2 times of P. So, this will be equal to 2 into 2P, or this will be equal to 4P. This is suppose equation number 4. Similarly, considering pulley number 3, what we will get is T4 is equal to 2T3 is equal to 2 into 4P, which is equal to 8P, or you can say 2 cube P. This is suppose equation number 5. Clear or not? Okay. Now coming to this equation, T1 plus T2 plus T3 up to Tn is equal to W. Okay. So, what we will get? Okay. So, just put the values. So, we will have what? T1 is P plus 2P plus 2 square P plus 2 cube P plus and so on. This will be equal to W up to Tn, okay, or you can say 2 raised power n into P. Okay. So, this will be equal to P into 1 plus 2 square plus 2 cube up to 2 raised power n is equal to W, or you can say W by P is equal to 1 plus 2 square plus up to 2 raised power n. Okay. So, what will be the summation of this? So, this will be equal to W by P is nothing but mechanical advantage. This will be equal to 2 raised power n minus 1 upon n minus 1, as we all know. Okay. Oh, sorry, 2 raised power n minus 1 upon 2 minus 1. Okay. So, this 2 raised power 2 n minus 1 upon 1. So, this mechanical advantage will be equal to 2 raised power n minus 1. This is the mechanical advantage for this particular system. And as we are assuming the frictionless pulley, so velocity ratio will also be equal to 2 raised power n minus 1. That is it. Okay. So, this is about third system of pulley. For ideal machine, the mechanical advantage will be equal to velocity ratio, which is equal to 2 raised power n minus 1. Getting this or not? Okay. Okay. So, now we will solve few questions related to pulleys. There are 3 pulleys arranged in the third system. Find the effort required to lift a load of 500 Newton if the efficiency of pulley system is 80%. Okay, so we have the third system of pulley, and as we know that third system of pulley, for third system of pulley velocity ratio just we have seen is equal to 2 raised to power n minus 1. Okay, n here is given as 5, sorry, n here is given as 3 pulleys are arranged in the third system. Okay, so from here we can get the value of velocity ratio, this will be equal to 2 raised to power 3 minus 1, which is equal to 7. Okay, now ideal load as we know is equal to what? W upon velocity ratio. Okay, the weight which is to be lifted, the load is 500 Newton divided by velocity ratio is 7. So, this will be equal to 71.42 Newton. Okay, this is the ideal weight to be applied. Now, what about the actual weight? So, efficiency is equal to, since actual weight will be more than that of the ideal weight. So, efficiency is equal to P ideal upon P actual. So, P actual will be equal to P ideal upon efficiency. So, this will be equal to 71.42 upon efficiency is given as 80%, 0.8. So, this will be equal to 89.3 Newton. That is it, answer. Getting this or not? Okay. Next question. In first system of pulleys, there are 4 movable pulleys. If an effort of 100 Newton lifts a load of 1360 Newton, find first effort wasted in friction, second load wasted in friction. Okay. Okay. So, we have first system of pulleys, okay, and as we all know that for first system of pulley velocity ratio is equal to 2 raised to power n. Okay. N here is given as 4 movable pulley, number of movable pulleys are 4. Okay. So, velocity ratio is equal to 2 raised to power 4, which is equal to 16, clear or not? Okay. Now, we have to determine the effort lost in friction and load lost in friction. For that, obviously, we will have to determine P ideal and W ideal. Okay. And as we know that P ideal is what? W by velocity ratio. Okay. W is given as 1360 Newton divided by velocity ratio is 16. So, from here this P ideal will be equal to 85 Newton. Okay. Now, what will be P friction? Effort loss due to friction, this will be equal to P actual minus P ideal. Okay. Now, in the question the effort given is 100 Newton, that is actually the actual effort. Okay. So, this will be equal to 100 minus 85, which is equal to 15 Newton. Answer of part A. Okay. Now, what is the part B saying? Load loss due to friction. Same thing, we will have to determine ideal load, W ideal, and how can we determine W ideal? Again we know the formula is equal to P into velocity ratio. Okay. So, P actual is given as 100 Newton. So, this will be 100 into velocity ratio we have determined as 16. So, this will be equal to 1600 Newton. This is the ideal load to be lifted, which would have been lifted. Okay. So, from here we can determine W friction, which is equal to W ideal minus W actual. So, this is equal to 1600, W actual is given as 1360. So, this will be equal to 240 Newton, that is it. Okay. So, this completes our pulley part.